Hey, good morning, and thank you for showing up. Before I get started, maybe like one question. So who of you came because you think the title of this talk is awesome? Okay, well. And who came because I think that the title is not good, but the content is interesting? No. So the title was generated by ChatGPT. I wrote an abstract and art. What would be nice title, but I was now unhappy with it. Okay, and the second thing that, are you coming to me? Okay, so, hi, that's my son Alex. So, the second thing is I have a Lego set to give away. So whoever manages to stay awake through the whole talk and will be able, I will ask one simple question, whoever is able to answer this question will win this Lego set. If Alex doesn't open it first, let's see if it works. Yeah. So, okay. With that, I hope the title by the end of the talk will make sense. This is a journey, like I tell you a little bit of the journey about building a medical, like a cancer research platform in Europe, so working with patient data, what we had to do to be able to do that, and then how we improved it to also to be able to work with normally, like agile and stuff again. So my name is Florian. I work for a company that's called Flatiron Health. And as I mentioned, what we're doing, we're building a cancer research platform. I will talk about this, what this means in a second. But first, the content. First, I want to introduce you a little bit to what we're doing. And this is all centered around real-world data, real-world evidence. Does anyone know what real-world evidence is? Oh, okay. That's great, because so when I start, I never heard about this. I never heard this before I started working there. So I explain it to everyone, if they ask or not. Then I will talk a little bit about why it's not so simple to generate real-world evidence. So what are the particular challenges? Then I will talk a little bit about feedback loops. So what's also in our case important, what you do probably every day on every basis, getting feedback, talking with colleagues, and also how it looks in our case. Then I will introduce a little bit our technology stack, and then I will introduce some of the improvements that we implemented to speed up the feedback loops. And lastly, I will close a little bit with the impact on what all of this has on the generation of real-world evidence. Okay, let's get started. What is real-world evidence? So the first thing, so real-world evidence, the idea is that when we go to the hospital, when you go to a doctor, all kinds of data is recorded about ourselves. Just doctor notes, like the doctor writes, okay, the patient was there, he doesn't feel well, I will increase the dosage of that medicine. So this is real-world data sitting there in systems that are not built for research, mainly in documents, free text fields, unstructured. And it's spread across very different systems that are not built to operate together, and are not built for interoperability. But why does it matter? Why do we think about this? Because like drug development or medical research is slow in general, like especially when you're coming from IT, you have like cycles of 15 years to develop a new drug. So, and as I mentioned, we're focused on cancer research, so we're building a cancer research platform. In oncology, it takes 15 years, hundreds of millions of dollars, up to $1 billion to develop a new cancer drug. And you can really see this in the beginning of the year. There's a large life science company from Germany called Bayer. They had to stop the drug development after the third clinical trial, and the stock prices dropped by 20%, just to see what an impact this has on the company and how expensive this is. Data is not the only reason that makes this expensive, but it's one reason. I suppose all the clinical trials is very hard to do. And the idea of real-world evidence is now to replace some of those clinical trials, basically to provide data that researchers can use to do early-stage researches, but also later on for clinical trials to prove the effectiveness of a drug, to also get for approvals in different markets. So the main aim of real-world data is to speed up the development of new drugs and also to make it cheaper. But second of all, and this for me a bit more important, it has to do with the population groups that you're able to represent in real-world data. And nowadays, so I don't have a medical background, right? Everything what I tell you about cancer, I learned, on the job. But one of the things that was very interesting for me to learn is nowadays, when people have cancer, their chance to survive, and it's also important to have a good life after the chemotherapy, are much higher. And one of the reasons why this is nowadays much better is that the researchers realized that cancer is not a single disease, it's a collection of 1,000 diseases. It's a collection of 1,000 very different diseases, and modern chemotherapy is very targeted. And it's so targeted that it actually behaves differently amongst different population groups. And those are so important that you're able to map different people with different backgrounds, not only different origins, but different life stories in your data to see the impact of a drug on their treatment. Okay. That's the story about real-world evidence, and I hope I could motivate a little bit that you also agree with me that it makes sense to work on that. But of course, it's not easy. I would not be standing here if it would be easy, right? The first thing is, we're working in with medical systems, and medical systems, like those kinds of operational systems, they are built for interacting with an insurance. They are building basically to keep the operations up in the hospital. They are not built for capturing research data. It starts with most of the relevant data is in free text fields, right? I mean, there are structured fields like the birth date and maybe a diagnosis code. The rest is free text field, completely unstructured. And this data comes in all different shapes and silos. There are standards, and there are a million of standards, and it feels like every hospital has their own standard. But if it has standard, it's a good thing, even with a million different ones. But most of the time, you just get a dump of a database, right? Like internal data schemas from an operational database. And then you need to basically build your own data standard. The next thing, of course, that I mentioned, most of the data that's important for research is not in a structured way, right? It sits in documents. So we have to do a lot of document pressing, a lot of natural language processing. This is an example. This is generated. That's not real patient data, but that's a typical example how the data is presented to us. It's really like a note, often just spoken, right? It's like also an audio recording that a doctor just gives a note. You all know that when you go to a doctor, it's not that the doctor sits there for 45 minutes and rethinks everything that they told you. Basically, they record their observations, and then comes the next patient. And that's the data that you get. And the last thing, which matters for the talk also a lot, is, of course, we're dealing with very sensitive data. We're processing patient data. And especially we do this in Europe. And in order to do this, we need to build a lot of boundaries and different systems in order to be able to do that. And in general, I want to show you a high level how the architecture looks. So the reason why we can't do this in Europe is because we have a very fragmented system architecture. And what we say, we have privacy-enhancing data processing stages, and the privacy level increases from left to right. So the very dark area, these are the hospital areas. That can be, sometimes we put servers into basements. Sometimes we operate with hospitals that have their own data center, and we deploy software there. But in general, this runs on the premises, like some pre-processing, the data extraction and pre-processing on the premises of the hospital. Then comes the layer grade area. What we do next is we want to move the data to the cloud as soon as possible. Right? So we basically remove direct identifiers, names, addresses, insurance numbers, things like that. Then when we move it to the cloud, but this cloud environment, we build up one cloud environment per hospital, where by GDPR, they are the data controller, we are the data processors. So we act like an IT shop for this hospital. We build up a cloud environment, they control the data. Then we process the data further there until it's more anonymized. Then we move it into a central environment where we are the data controllers, and we are able to union all the data from all the hospitals together. Then we do the document processing and further enhancements and developing our final data models. And lastly, this layer on the right side is the data serving. We give access to our data to our customers, which are life science companies, in an environment where we control access. So only then the data is considered to be fully anonymous. So we removed all the identifiers, we shifted around the dates, Plus, we control what the people do with the data. So we're able that they don't link the data to other data sets they're not supposed to do. Okay. I hope you're a little bit scared and you don't think, I will do this tomorrow myself. So it's a long journey. But still, I mean, we're doing software like data engineering, data science. So we have the problems that probably every one of you also have, right? We don't build systems and 3 years later we will find out if it works or not. We are like temperament and we need to do experiments, we need to try things out, we need to get feedback. And the most important stakeholder group in our company are clinicians. So we are like doctors, from oncology nurses, like working full-time for us. It's like a very important group, but they are very busy, right? It's not that they send in, we have a doctor at every team and it's available for asking questions all the time. But this is a very important group in our company. Then, of course, we have data scientists, another important group, and then people like me, engineers. And all three functions have to work together, right? To improve the system, to build the system, to improve the system. So these are different functions, and especially cross-functional teams don't work really well with clinicians. Not because they don't want to, but they're rare, right? You cannot put a doctor in every team. Plus, this all happens in a very fragmented system where there is not one system that gives you access to all the data. You have to constantly switch between systems, log out of this system, log into this system. That makes everything very slow and hard. And I'll give you maybe an example of an issue that we had, which we found very late. So whereas we got new data, we extracted new data, everything looked good, right? So because the matrix that can calculate early on look good. Like there are more patients, the data volume increased how we would expect that. And then the data is transformed until it hits our models, and then we could extract like a medical treatment plan. So basically the journey of a chemotherapy. And what we noticed, it looks like as the hospital stopped working in January. So the curve of medication administration, so like the chemotherapy was like a logistic downfall. Like basically was the curve was going out like this, as if the clinic stopped giving chemotherapy. And this is like tiny fraction of the data. We didn't notice this early on, and the reason is the hospital switched to a new system to manage those chemotherapy, and it didn't tell us about. But nothing of the early stage data indicated that. And it took us 3 weeks or so until the data was processed for all the stages, until we were able to run those tests. And then 3 weeks later, we need to come back to the hospital and ask, hey, can you help us? And the IT in the hospital is not working for us, right? You also need to write an email, wait for an answer, things like that, right? That makes everything very slow. So this is one of the problems we were facing, and where we realized, okay, we really need to improve something. Okay, and before I can tell you how we improve things, I want to motivate a little bit, or explain you a little bit how our data architecture looks. And before I talk about this, so I think it's a little bit smart of myself, so I will explain you data architecture with Lego bricks, and I have a Lego architecture set as a giveaway. I mean, I'm a bit proud of that. I'm also proud of those animations. I did them myself. So, okay, so we're running on AWS, right? I mean, not only, like Flatiron is not a small company, so everything what I tell you can imagine we have 10 different versions of it, but largely we run on AWS. Then we use Dexter for data orchestration. We also use Airflow, right? But for this part of the platform that I'm talking about, we're using Dexter for data orchestration. Who of you has heard of Dexter before? Okay, awesome. I will talk about this a little bit more later. Use DLT for extracting and normalizing data. Same question. Who of you has heard about DLT? Also awesome. I will also talk about this. Then we use DBT for data transformations, and we use Snowflake as our data platform. So that's a typical data stack for us, for our data platform. And I want to show you just some examples, or like some example code, how this whole, to get a feeling how this looks. So we use Poetry, so we install all the packages. So we install Dexter, DBT, DLT, and IBIS. But first, let's look a little bit what those technologies are. So Dexter is a data orchestration tool. So it's an orchestration tool, like many orchestration tools, like Jenkins, TeamCity, but purposely built for data. So a bit more like Airflow. And what the reason why we use Dexter in this context, this is the only like professional orchestration tool that I know that has an in-process mode. You cannot run it without infrastructure. Typically for an orchestration tool, it captures state, right? It manages the pipeline runs for you. So it's a database, it has a UI, you need a web server, you need an execution cluster, like a Kubernetes cluster, things like that. Dexter has all of that, but you can run Dexter as a command line tool. So you basically can take a Python file and just do Dexter run without any infrastructure. That matters a lot, and hopefully by the end of the talk you will understand why. So this is, and it has a great integration into the Python data stack. So it has a great integration with dbt, but many of those tools have nowadays. Okay, dbt. Who of you has heard of dbt before? Okay, cool. So dbt is a tool that makes SQL development sane. So basically what the dbt project looks like, it's a lot of SQL code. They're using Ginger as a templating engine, and they're able to connect those SQL codes, they understand the dependencies, and they're basically taking those SQL files and build a pipeline out of that. That's really built for transformations. My recommendation is you should not use dbt for anything else, because then it gets very messy, but it's really good for doing SQL-based data transformations. There are alternatives nowadays, like SQL Mesh, but dbt is a great tool for that. Next comes DLT. I already asked about who knows DLT. The story about DLT is it's very funny for me because I met them 1 year ago at this conference at EuroPython. Back then we had like our own home-written data loading and ingestion tool, and I was in charge of documenting it. And I saw the folks from DLT, and I thought, they're doing the same thing, and this frees me from having to write documentation, so I will use a hackathon to try it out. And it actually worked great. So what they're doing is, you can point DLT at any kind of data source, like ingestion tools, like Fivetran and all those big tools, a database, an API. They understand a lot of dialects. What they do is they extract the data stateful, so they remember state, that they can retry. They also support incrementals. And then what's very important for us, they normalize the data, because typically data what we get is hierarchical data. So XML, JSON, things like that. And what DLT does, it normalizes that into a relational model. So like really think like old school database normalization, second, third normal form, which is better suited for downstream analytical processing. And DLT does this in a very reasonable way for you. You don't have to write this code yourself. And the side story of this journey of DLT with us is before we were running classical pattern, we were loading raw data into Snowflake and doing the normalization in Snowflake. And our data is like we have text data embedded in JSONs, things like that. So we have JSON files that are 40 megabytes per patient. Normalizing those JSONs is the most expensive thing you can do in Snowflake. And DLT does this outside of the data warehouse. So it first extracts the data, normalizes it, and then loads it in the data warehouse. And overnight, the performance degraded maybe by 5% or 10%, so not really much. But the pipeline costs dropped by 50%. Because it turned out that the normalization of those big JSONs was the most expensive thing what we were doing in Snowflake. Snowflake is a great tool, but processing JSONs is probably the most expensive way to handle JSONs. And lastly, we're using IBIS. Did anyone hear of you about IBIS? Also great. So IBIS is a neat framework that builds an abstraction layer over, so it's a data frame API, so like pandas, you can write pandas style code. But it's an abstraction over many different backends. So they have integrations with Snowflake, with Databricks, with all your databases, not pandas, but polars. And what basically allows you to do, you can write backend agnostic data frame code. So you can write Python code, and it works the same across many different data backends. This also matters a lot for us. So right now, this tech stack uses Snowflake. You could just write Snowflake native data frame code, which would be Snowpark. It's like the data frame API of Snowflake. But we use IBIS, and hopefully the reason for that will become clearer later on. Okay, we use, as I said, we use Dexter, so let's write together a pipeline. So you need one definitions file or pipeline Python file. And the concept of Dexter is assets. So basically everything what does something, with the data is an asset. You declare an asset with a decorator, so those add asset decorators. The first thing what we're doing here, we use DLT to load and transform data. So we need a DLT source, which basically reads files from somewhere. In this case, it's from S3. These files, in this examples are BDT files, is a horrible data standard from Germany from the late 80s. So it's really like, if you really want to see all data standards, you should work in the medical sphere because they never disappear. It's like a line-based data format. Each line has the number of bytes in this line, right? Then there's some delimiters, and then you have like a field number, and it's a tree data structure expressed in a line-based data structure. So we use the BDT transformer. We use the BDT transformer to turn this into a JSON that DLT understands and that DLT can use to make nice tables out of that. We wrap all of this as a Dexter asset, and then we call a DLT pipeline, and the pipeline is declared as a DLT resource. A DLT resource is basically a thing that DLT can inject into functions, so you can replace it when you run a write unit tests for that. And here we basically point DLT to Snowflake. The credentials are coming from environment variables, and this is really, I left something out, but this is more or less production code. So this runs in production and does its job. So it's just a couple of lines of Python code. So now we have the data extraction, the data normalization, and the data loading. Now we need the data transformations, and we're using DBT for that. Tables are represented in DBT as YAML files. You will write a lot of YAML files, right, with using DBT, but I believe with every other technology nowadays as well. So you declare tables. So the output of DLT will be the input for DBT, and you declare them in YAML files. And what Dexter needs is some metadata, and DBT allows you to annotate tables with metadata. In this case, we basically put an asset key there, so that Dexter is able to connect the DBT models with the DLT tables. So that Dexter understands that those two things belong together. We need to turn those DBT sources into Dexter assets. These are no-op assets. We basically, for each of those DBT sources, we create an asset that doesn't do anything. So there's a pass statement, just that because Dexter doesn't read the YAML files, Dexter needs a Python asset. And then we can write our SQL code. So DBT has a notion of models. So each SQL file in the models folder will be a node in the DBT DAG. So it's just a transformation. I think this is for a lab table. I left most off of that. Basically, we reference a couple of sources, we join them together, and then we apply some transformations to get some preliminary lab data out of that. And then DBT, we need to compile DBT, which is like a false friend because compilation really means running Ginger. So DBT does not compile SQL in any way. But we supply the profile Snowflake. The DBT knows, okay, we want to run this against Snowflake. So it compiles this with Snowflake in mind. I will also explain what this means later. And then lastly, we wrap the whole execution of DBT in a Dexter asset. It's just 3 lines of Python because Dexter has a DBT integration. That's a very nice thing. And then we use IBIS for some post-processing. So we are using SQL for extracting the lab data, and then using here IBIS for running some Python code. So you can think of invoking a model with that, right? Or like piping the data to an LLM, for example. Yeah, so for that we use IBIS. IBIS has a very great function to pandas patches. That basically it patches the data on the data warehouse side, and then you basically get it in like a data frame chunk so that you don't overload your memory. That works very smoothly. Okay. And lastly, we wrap everything together into a Dexter definitions object, and that we can run. So as I said, Dexter has a server, right? Dexter has a database, it has a UI, so there's an option you can click a button to run a pipeline. For us, it's important that we can run it wrapped inside a Docker container, just as a CLI invocation, and we basically call the materialize command. We point the materialize command to this Python definitions file, and that runs the pipeline. And what we did is, it looks a little bit like this. So we have an extraction, we use DLT for extracting the data. In our case, it's just those BDT files, text-based files. DLT extracts them, we transform them into a JSON structure, then DLT uses JSON structures to create tables from that and load those tables into Snowflake. Then DBT takes over, applies SQL transformations, and then we use IBIS, a Python asset, where I think that model that I showed you does harmonize the lab data, because what we have to do is every laboratory on the planet has their own, I mean, that's not true, there are standards, but you can assume their own way of notation, their own codes, and we need to unify all that. This is like a process called harmonization, and so you have a model for us to do this, and this was the Python code that I showed you that invokes this model. And then we have, at the end of the stage, a harmonized lab table that basically has all the bioparameters of our patients in a harmonized way. Okay, that is like how we worked. Let's say how we worked by the end of last year. And now I want to talk a little bit about the problems, or like maybe like repeat the problems that we had and talk a little bit about what we did to improve the problems. So the first problem I already mentioned, right? That we needed to really transform the data, that we get a data model that we understand, so we can apply meaningful data tests on those raw data, those BDT files. You cannot, I mean, you can do some integrity tests, you can some counts, but you cannot really test, for example, the distribution of a certain drug over time. So we have things like, okay, for a person with breast cancer, we would expect that 70% of those patients in Germany have that drug, right? If that's not the case, something is off, because that's the absolute standard drug, and that means something, maybe we're missing some data, or like the hospital, you know, has maybe some weird treatment pattern, or like some unusual treatment patterns, but things that we need to know. But those tests you can just run very late on our pipeline. So one big strategy in our company is to shift testing left. And the way how we do this, anyone, if you're familiar with like the classical testing pyramid, yeah, so that's like, that comes from, I think, software engineering more, that you basically have the idea that, okay, you have a lot of unit tests, like easy to run tests, then less integration tests, where you need some infrastructure, and just a few end-to-end tests or smoke tests. If we translate this, of course, most of our pipelines are Python code. So like unit testing Python code is, so to say, just like easy, right? So we always try, you know, to write our code in such a way that's easy to unit test. Then, of course, we have a lot of SQL code. SQL unit tests is like a thing. There are tools like SQL Glob that allow you to run SQL locally, but typically to really unit test SQL, you need to run it in a database, so you could argue if this is still a unit test. Then we have integrity tests, we have regression tests that check how the data develops over time. And lastly, we have cohort tests that basically are statistical tests on a cohort level. And I want to show you how one of those core tests looks, that we shifted left. So initially, those core tests were scripts written in R, actually. By the end of our pipeline, we had like medical experts that we had tests run, like R scripts running, creating a report, and we had medical experts looking at those reports. And then with that, we identified unusual patterns that hinted at a problem. And then what we did is we basically turned those discoveries by people into automated tests using DBT. And DBT has a great feature. These are running data tests. So if we look at our John Doe Clinic lab YAML file, so you can add a data test section on a content level. So this is a home-written test. So basically, just expect row count quantiles to be greater than or equal to. This is a SQL snippet that lies somewhere in our code base, right? It can be parameterized, but it's not too complicated. So what it does is, for the column test, and this means lab test, first we filter out for certain drag names, then we filter out certain patients, and then we expect a statistical distribution. For example, like for every, as I said, for 70% of breast patient cancers, we expect that they got this drug over time every 2 months. Things like, and this is not the case. It might be that data is correct, but at least we want to be alerted on that if we don't see this pattern in the data. And in the cases earlier, as I mentioned, this is crucial for us, for example, to detect that, the hospital switched, introduced a new IT system, and suddenly the data that records this specific drug is not there anymore. And it's also super important, because if you would not detect this, you would create biased data. and which is of course like not good for medical research. Okay, the shifting data test left is like was the first crucial pattern. The second crucial pattern is that we want to bring our pipelines to a notebook environment, so an environment where data scientists work and can collaborate with the clinicians. So the way how we do that is, so basically what you do is we replace AWS, your Kubernetes cluster, with a Jupyter notebook. It's a little bit a joke, right? But you can imagine like this, that our pipelines, we are able to run our pipelines in Jupyter. And the way how we do that is rather straightforward. So we add the IPY kernel dependency, and from that IPY kernel dependency, we then install our Python project into that kernel. So you have your data pipeline as a Python package available in the Jupyter kernel and can just import it. And so we're using SageMaker for that. If we head over to SageMaker, what we can do now with that, so we import all the Dexter and we import this definitions file, we import the pipeline. And then what we're able to do is we redeclare one asset. So in this case, the harmonized asset, let's say we want to prototype something, we want to switch the code, and then we're able to run the pipeline to see what comes out, what happens with that. And this is done by data scientists and clinicians together, where basically experiment and prototype on a transformation to see if we can decrease the missingness by applying some other transformations. And we see, like not in real time, but it takes some minutes that they get a result and not a day or two. So that's basically creating an environment where data scientists and clinicians can work together. And lastly, the last important pattern is all of that should happen. So the testing, the collaboration between data scientists and clinicians should happen as soon as possible. So even in those restricted environments. And for that, we need to make our pipelines portable, because Snowflake does not run in a data center of hospital. I think you can pay Snowflake a lot of money that they would allow you doing this, but this is not what we want to do. So what you basically need to do is to make our data stack really portable is to replace Snowflake. And what we do is we replace Snowflake with DuckDB. Who of you has heard of DuckDB before? Yeah, awesome. So DuckDB is, so first, I mean, we add all the dependencies like the DuckDB flavor of DBT, DuckDB as extension of DLT and so on and so forth. And DuckDB is an in-memory or file-based analytical database. So like something like SQLite, but for analytical purposes. And it's very interesting is like the performance, depending on the machine you're running, is on par with the Databricks and Snowflake. So if you give it a large enough machine, the queries run comparably fast. But you can also run it on a much larger laptop. And I would argue, I mean, we're not working with big data, right? I could process the data on my laptop. I'm not allowed to, right? But I could. So it's basically, I don't need Snowflake because of the data volume. Snowflake has a lot of features, but in this area of where like the machines that are cheap are large, fast enough, I think systems like DuckDB are a great alternative. That you can basically build your own data platform as a Python package. Okay. So we use DuckDB to make this whole portable. So in order to do this, first of all, we need to point DLT not to Snowflake, but to DuckDB, and it's as easy to replace the string Snowflake with DuckDB. And then DLT will handle the rest for you. Next, we need to change a little bit of transformations, because as awesome as SQL is, it's very hard to write database agnostic SQL code, right? Especially when it comes to data transformations, JSON processing, regex structures. DBT has a feature, there's a dispatch mechanism. So instead of calling the toDate function with a Snowflake SQL function, we call a macro. And DBT then has a dispatch mechanism. We basically implement a toDate macro, and then DBT will dispatch the implementation to a backend specific implementation. So in this case, we have a DuckDB toDate function where we basically emulate the functionality of Snowflake's toDate on DuckDB. We have to do, I mean, in total we have maybe 20 of those macros. So typically we try to write standard SQL, but sometimes, especially when you're processing JSON, it's not possible, but it's also not too crazy. I want to say that there's alternatives, like SQL Mesh is a competitor of DBT that uses SQL Glot, which compiles SQL and does this for you. But we're using DBT and therefore using this dispatch mechanism. Okay. And lastly, IBIS, we do the same thing with DLT. We point IBIS now to DuckDB instead of Snowflake. And since IBIS makes it easy for you, that data frame code runs the same, right? You just switch the backend from Snowflake to DuckDB, and we don't have to change the IBIS code. The data frames work the same. Then we wrap everything up as a DAXA definitions. One note, because DuckDB is file-based database, we need to switch the concurrency model from in-process executor, because DuckDB holds logs, right? So you cannot connect to a DuckDB file from two processes in parallel. So we basically need to run the pipeline sequentially, but since this is like a pipeline that runs on the server in the hospital, it's just a fraction of the data, that's not a problem for us. And what we achieved now with putting everything together, basically, I showed you this part of our pipeline where I basically take the raw data, extract it, normalize it, load it, harmonize it, and we're able to move this data into the AWS environments owned by the clinics totally, or even on-prem on the servers or the data centers that are running the hospitals. And all this together with a Jupyter notebook that basically we can log into the hospital system, open up a Jupyter notebook, our clinicians and the data scientists can look at the data early on, that we start very early the investigations or finding issues. Okay, lastly, I have to speed up a little bit. The impact of real-world evidence generation. I think the numbers, so I hope the numbers speak for itself. So our data has been used in over 1,200 publications, and it is considered a golden standard for real-world data and cancer research. And one reason is because we have very specific data models. We invest a lot into building the data models, into deep data models, which is a lot of effort, but it's also possible because we're able to iterate faster. And this was a paper, I think it's published in the beginning of the year. I think it just summarizes this greatly, and it's also a great motivation for me that doing all of that benefits patients worldwide by ensuring that high-quality real-world data can inform clinical decisions and health policies on a global scale. With that, I want to thank you so much for your attention, and I'm not sure if I have time for questions. Thank you.
Thank you, Florian, for this wonderful talk. So we have a question answer timing. So if there is any question, please feel free to raise your hand.
Cool. Before, while you're working, I maybe, as I promised, I will ask more questions. Okay, like to win the Lego set. Which database do we use to replace Snowflake? Okay, I failed to see who's last, so. Who was first? Hast du zugehört? Okay. Who was first, honest? Okay, then, okay, schau mal, jetzt kannst du das Lego zu den Menschen in den weißen Pullover bringen. Okay. 1 second, maybe you can ask the questions already, I will help you.
Okay, thank you. Thanks a lot. It was very interesting. So my question is about the data losses that you potentially have, I guess, because the initial data is so raw that when you transform, you might lose something. How do you know about it? How you getting where, and what do you do afterwards? Like if there is the data that's your pipeline is unable to process, what's the workaround for you? So
largely we know about this through the cohort tests. I mean, sometimes integrity tests, sometimes you know that certain data has to be there, but it's most of the time not the data. It's mainly through those cohort tests, through those statistical distribution tests that we basically expect through like just experience, right, from our clinical staff, that you have certain expectations. When if someone has a certain cancer type, we expect that certain tests are made, right? And if we don't see the distribution of the test, then we typically is a hint that something's missing. An example for that is like the harmonization issue. when a new lab introduces a new test, it's not in our harmonization standards, and when it's not harmonized, it's lost. But we discover that because we also have researchers, right, and they basically know what is the current up-to-date treatment plan. So we expect to see this in our data, and if we don't see that, then we basically investigate. And then what to do really depends on, in that case, we needed to update our harmonization routine. Basically, we need to check. Sometimes we just analyze the data ourselves. Sometimes we need to reach out to understand, hey, there's this new test. Do you use it? How do you represent this in your data? And then we need to update our code. Sometimes we just remove patients from our data set. So what we do not do is basically if we see that something is inconclusive about patients, we do not include those patients into our data sets. Does it answer the question? Okay, perfect, thanks.
Okay, so who is the next one?
Yes, thank you for the talk. I had actually kind of two questions. The first one is actually because about the privacy thing, how do you recognize or take off data that is privacy related? So I don't know how far it's important for you, but the names, I can imagine being different data sources. Do you combine first and last name, these kind of things? And also a bit related, how do you make sure, or do you have, I can imagine even a data set or the data about one patient coming from various data sources, how can you make sure that it actually results in only one point of data, make it kind of unique? Do you have a pseudonymization maybe algorithm based on the name or something like this to identify? Maybe it's even not a problem in your case, I don't know, but you may have that coming from two data sources, data from one single patient, and to avoid to count it two or multiple times.
Okay, so the first question is that it depends on the country, because we operate in the US, in Germany, in UK, and Japan, and what we do really depends on the local regulations. And I give you two examples. The first thing, in Germany it's a bit easier, surprisingly, because in the first stage we have access to all the data. So we know the patient names, we know the numbers, right, in the very first stage, and we can use this to pre-anonymize the data. We have a fuzzy model for that. It basically searches for combinations of names, but we know what data to look for, right? That makes it, of course, easier. In UK, it's not the case. So where we don't get the master data, there we use a technology called John Snow Labs that basically, I believe it's just an entity recognition system that basically looks for names and patient IDs and text documents and relationships, and we're using that for redacting documents. But I don't know so much about that approach. I can largely comment on Germany, and that's rather easy because we know the data that needs to be removed. And the second thing is also the boring answer. We simply don't. So by default, we only can, by definition, we can only combine the data of two systems if it's anonymized. If you would be able to see it's the same patient, they would not be anonymized anymore. So if it happens that you have patient data from two different hospitals, it's two different patients. Yeah. So it's a disclaimer on our data, but it would break the anonymization requirements, right? If you would be able to do that, the data would not be anonymous. Okay. Yeah.
Thank you very much. I'm from New Zealand, which is everybody asking me how I managed to come here. My question is, I'm doing exactly the same project, even though I'm not an engineer and not a scientist or anything. I'm running the endometrial cancer and trying to understand the journey, the whole journey. Cool. There is about the privacy issue. Some of the reports, even if you take care of everything to try to anonymize it, there is a hidden information somewhere in one of the reports which might be jeopardize the whole privacy. Like in the lab report, you might find the national health number and the address and the name of the doctors and the name of the patient. How to deal with this thing?
So I have two answers for that. So first, amazing. Also, maybe you can have a chat afterwards. And and yes, how did you come from New Zealand here? But maybe the first thing is most of our data is categorical data. So all our models map the data to a predefined value set. So that so the output of the model will never be a like insurance number or stuff like that, because we basically most of the data is really categorical data or like numerical data. So if we like have a certain lab value, so 4.0. But still, right, you're right. So anonymization is a very difficult topic, right? And there are a million different definitions what this means. The last thing is like the trusted system in which we allow our life science partners to work with data, like this is called a trusted research environment, where we control what the people do with the data. They cannot download it, they cannot upload any other data sources, they have to work in there. So that even, let's say a certain cancer type is very rare, combined with if patients are very old, we truncate the date of death to the last 5 years, something like that, right? But even that can give you a hint for very rare cases. If you combine it with other data, that you could identify patients if you combine this with demographical data from somewhere else. So this is like important that we have an environment where basically we ensure we can control that people don't do that. By just looking at the data, you'll not be able to know who it is. Probably by linking this data to other data, you could. So we have a system that basically makes this impossible to do that.
Okay, we are out of time. Sorry, I cannot take more questions. So please give him a round of applause for Florian. So that was a wonderful talk. Thank you.